All right, so let's get right into it. You look up at the night sky, you see all those brilliant points of light, but have you ever really stopped to think about where they come from? Well, the answer, and this might sound a little crazy, is from complete, total darkness. And that right there, that's the big paradox we're talking about today. I mean, think about it. The most dazzling, brilliant things in the entire universe, they all start out in these places that are so jam-packed with gas and dust that not a single photon of light can get out. It's like a rule of the cosmos. The brighter the star is going to be, the darker the place it's born.
So that's our big question for this explainer, right? What flips that switch? How do you go from a cold, dead silent cloud of gas to a raging nuclear furnace? I mean, what actually makes a star light up?
Okay, so to get to the bottom of this, we've got to go right back to the beginning. We need to go to where the stars are born. And that means heading into these enormous, completely invisible pockets of space. We call them stellar nurseries. The proper name for them is molecular clouds. And you have to understand, these things are the raw ingredients for, well, for everything that comes next. So whatever you think you see when you look up at night, forget it. The real story starts right here, totally hidden from our eyes. And let me tell you, the conditions inside these clouds are wild. We're talking unbelievably cold, like just a tiny bit warmer than absolute zero, the coldest it can possibly get. They're made of pretty much nothing but hydrogen gas, and they can stretch for hundreds of light years. It's no exaggeration to say these are the quietest, coldest, and you guessed it, darkest spots in the entire galaxy. So how does anything even happen in a place like that? Well, it all starts with just a little nudge, a cosmic whisper, you could say. Maybe a shockwave from a star that exploded millions of years ago passes through, or maybe just the gravity from another star passing by. All it does is create one little spot in the cloud that's just a tiny bit denser than the rest. And in space, that's all it takes. Because density is destiny. The second that happens, gravity gets its hooks in and the whole thing starts to collapse. But you know, this collapse isn't some smooth, simple process. Not at all. The moment it kicks off, this epic battle starts up. A cosmic tug-of-war between two fundamental forces of the universe. So on one team, you've got gravity, and its only goal is to pull everything inward, to crush it all together. But on the other team, you've got pressure. See, as gravity squeezes all that gas, the little particles inside start bumping into each other like crazy. That creates heat, which creates an outward push, fighting back against gravity's pull. So it's this constant battle, crush versus expand. And what you get in the middle of this fight is something we call a protostar. It's basically the super hot, super dense core of this collapsing cloud. And here's the crucial part. It's glowing, for sure, but it's not a star yet. It's glowing for the same reason a bicycle pump gets hot when you use it, from pressure and friction. It's glowing from the heat of being squeezed by gravity. The engine hasn't actually turned on yet. Now, while this core is getting hotter and hotter, all the gas and dust around it doesn't just fall straight in. As it gets pulled in, it starts to spin faster and faster, kind of like a figure skater pulling their arms in. And this spinning flattens all that material into a huge disk. And this isn't just some leftover mess. No, this is what we call a protoplanetary disk. And that is exactly where planets are born. Our own solar system started out just like this. So the protostar just keeps getting bigger and bigger, pulling in more material. The core gets even hotter, even denser, and that tug of war we talked about, it is getting seriously intense now. We are right on the edge. We're approaching the moment of ignition. For now, gravity is still winning the fight. It's squeezing that core relentlessly. The pressure is building. The temperature is just rocketing upward. You just know something is about to break. And then, bam, it happens. The core hits a magic number, 10 million degrees Celsius. It's this incredible threshold where the laws of physics as we know them, they just completely change inside that core. What is it? It's nuclear fusion. For the very first time, the pressure and heat are so intense that hydrogen atoms are literally slammed together, fusing to become helium. And when that happens, it releases an unbelievable amount of energy. That switch we talked about, it just got flipped. The star's engine has just roared to life. And all that energy from fusion creates a brand new, incredibly powerful outward force. And when that outward push from fusion becomes strong enough to perfectly balance the inward pull of gravity, everything stops. The collapse halts. The tug of war ends in a perfect stalemate. And right there, in that moment of balance, a stable, shining star is born. But what kind of star does it become? See, the story doesn't play out the same way every time. It all comes down to one single thing: how much stuff, how much mass was in that original cloud to begin with. That one factor determines, well, everything.
Okay, so let's say there just wasn't enough gas and dust to begin with. In that case, the core never gets hot enough to start fusion. You end up with what we call a failed star, or a brown dwarf. Now, if you have a medium amount of stuff, kind of like the Goldilocks zone, you get a star like our sun, one that'll burn steadily for billions and billions of years. But what if you have a ton of mass?
Well, then you get a monster, a massive star. These things are the rock stars of the cosmos. They burn through their fuel at a furious pace, living for only a few million years before going out with the biggest bang imaginable, a supernova. We're talking an explosion so bright it can outshine its entire galaxy. And it's in those final, violent moments that the heavy elements, the stuff that makes up planets, and even you and me, are created and blasted out into space.
And here's a really cool thought. This whole process almost never happens by itself. Stars aren't born as lonely orphans. They're born in huge families, big clusters that all come from the same giant molecular cloud. Think about what that means. Our own sun, it probably has thousands of brothers and sisters out there, sibling stars that were born alongside it but have since drifted apart and scattered all across the Milky Way Galaxy.
So, this really changes how you look at the night sky, doesn't it? When you see those dark patches between the stars, you shouldn't think of them as empty space. You should see them for what they really are. And this isn't just theory. We can literally watch it happening. When you look at those breathtaking images of the pillars of creation, you are watching a stellar nursery at work. Hidden deep inside those dark, dusty columns of gas, new stars are being born right now as we speak. And really, that's the whole point. That's the big takeaway here. Darkness in space isn't emptiness. It's not a void. It's potential. It's a cradle, just waiting for gravity to give it that first little push to start the whole amazing process all over again. So, next time you're outside on a clear night and you look up at a star, any star, remember its story. Remember the long, silent journey it took from a cold, dark cloud. Remember that cosmic war between pressure and gravity. And remember that stars don't just pop into existence. They have to survive a relentless cosmic squeeze to earn the right to shine.